Hi there. Please do this physics practice problem. Great job. I knew you could do it. I always believe in you. I had these really cool spherical toys in school that I would like to show you, but unfortunately I can't. So check out this video. Wow, what a great video. Thanks, Mr. Lamb. You're welcome, buddies. Enjoy this physics lesson. Okay. The ball fell and hit the ground. One of them bounced back up. The other one stayed on the ground. So one thing we learned about last lesson was work. But I'm not going to talk about that right now. One thing you may have heard described in middle school or even elementary school is energy. These balls were moving. If the ball drops and hits the ground, then bounces back up, it has kinetic energy here and kinetic energy here. It had basically the same kinetic energy. You might even say it was conserved as a preview for later. But yeah, kinetic energy, kinetic energy. The bouncing ball, that makes sense. The ball that didn't bounce, it had kinetic energy, but then later it didn't. Maybe these bunnies though. Bunnies. What happened to the energy? Did you guys learn this in middle school? Yeah, it became sound energy. That's actually a really nice point. I couldn't tell in the video if you could tell, but whenever I do that with the two balls in the class, the bouncing ball makes much less sound. The ball that doesn't bounce, it makes a big like thump on the ground and it kind of shakes and vibrates. The energy is no longer kinetic. It became sound and vibration and other stuff. But that's not what we're talking about today. Today we're talking about physics stuff. So there's an idea of energy and it is related to work. Work we described last lesson. If you imagine a rock flowing through space, pushing it forward and making it go faster is positive work. Pushing it backward and making it slow down is negative work. So that's fine. We're still on that idea, but we're going to do some fancy math to see how much faster and how much slower it'll go. I did an example yesterday, but I wanted to start a new example, so let me do a new example. If I do, I mean copy from my notes. The example is here. A race car driving lamb is accelerated from rest. By a force of 81 newtons. Over a distance of 2 meters. This is a very small scale problem. That's fine. It starts off from rest. And it is only 9 kilograms, including the car. I picked these numbers for reasons that you guys don't have to worry about. Okay, find the final velocity. Find it the old-fashioned way. Find it the way that we do if we don't know anything about force and work. Wow, you guys did it already? That was really fast. Great job. You guys are so smart. We knew to take the net force over the mass, find the acceleration, and then, based on the initial velocity, we can find the final velocity from this formula. Starting from rest, so 2 times 9 times 2 meters, 36 meters squared per second squared is VF squared. VF equals 6 meters per second. Good job. Now, a totally unrelated problem. Find the work done on the car as it moves 2 meters. What? You're already done? Oh my gosh. You guys are the smartest bunnies. Good job, buddy. Good job. Work is FD cosine theta. And if the F and the D are in the same direction, theta, the angle between them, is 0. So it's just FD. 162 joules. Capital J is the unit for joules, as you guys know. Okay, why do we do these two completely unrelated problems? They're not unrelated, because then you have your mind blown. Yes? Yeah? Yeah? There's a cosine theta. Ignore it. Don't care about it. A nice mnemonic. If you're doing energy problems, it's mad work to do all these problems. Oh man, it's so much work. Oh, it's so hard to do because oh my gosh. It's mad work. You almost never use that, so don't bother. Is this useful? Will we ever need to find work over mass? Well, AD is something we saw over here also. So we can make a little substitution for no reason. This is VF, but I'll just call it V. Yeah, let's just say it's VF. Alright. And now, for no reason, I'm writing it like this. Okay, for most objects, mass is conserved. Mass doesn't change. When I'm running a race in a physics problem, I don't really lose that much weight until I go on a diet afterwards. So mass doesn't really change. We got work. We know its work is FD. Again, we're ignoring cosine theta for now. Assume F and D are in the same direction for this whole derivation. We know it's going to work. We found a new expression for work based on kinematics. It's 1/2 mv squared minus 1/2 mv naught squared. Well, 1/2 is constant, m is constant, this power 2 is constant. You can describe work as a change in a quantity, 1/2 mv squared. If an object is moving, it has mass m and it has velocity v. So it does have some number, 1/2 mv squared. We could have solved this like the first day of class. If you understand what mass is and what velocity is, you can find 1/2 mv squared. But there's going to be no point until now. Now it has an interesting significance. 1/2 mv squared, it doesn't really mean anything, but it is equal to W. Or W is equal to the change in this weird quantity, 1/2 mv squared. So because this quantity, just some weird algebraic combination of mass and velocity and math, we're going to give it a name. We're going to call it kinetic energy. If you guys have heard of energy in middle school, you know there's lots more types coming. But the first one we'll talk about, we already knew that pushing a rock in space will make it speed up or slow down based on the work done. Now we know how to find out the change in speed mathematically, because the work done is the change in kinetic energy. For an object in space with no friction, no air resistance, no gravity, nothing like that, this is true. In general, work is a change in energy. That's another physics definition of work. Whenever you do work on an object, you change its energy. I said when you do work on the rock in space, you make it speed up or slow down, you change its kinetic energy. We'll talk later. When I lift up my keyboard and the button on top, I'm doing work, I'm giving it another kind of energy. If I take my two hands and I rub them together, I'm doing some kind of work. My one hand is doing work in my other hands. I am giving my hands another kind of energy. We'll talk about later. For now, work can cause a change in the first and only kind of energy we know about, kinetic. And the amount of work done in joules is the amount of energy gained or lost or changed. So back in this problem with the Lamb race car, I did 162 joules of work. And we said the car went up to 6 meters per second. Is it true? Did it work? Well, I closed the problem, but you can take a glance at it if you know. It's right there. The initial kinetic energy, the initial value of 1/2 mv squared, was 0, because the initial velocity is 0. So, find the final kinetic energy. 1/2, the mass was 9 kilograms. The velocity was 6 meters per second. Nine, 18, 162 kilogram meters squared per second squared. Wait, 162 kilogram meters per second squared times meters? 162 Newton meters is also known as 162 joules, the same number as the work, and even the same units. So in that practice problem, the work done on that race car Lamb is equal to the change in kinetic energy of that race car Lamb. In more complex future problems, there'll be more kinds of energy, but in general, work is always a change in energy. And if no work is done, the amount of energy is constant. Yeah, lots of fancy math lesson. Hopefully went pretty quick compared to the ones I did last week. That's all I have to say about kinetic energy. You may have heard the formula ft cosine theta called a dot product in math class. If you did, great job. Keep on being super math scholars. If not, that's okay too. But we talked about work yesterday. If you push an object with force F over displacement D, you're doing work. Now we know when you're doing work, you're changing the object's energy.